the nth term test is one of the tests in identifying the limit of a certain series given that the series is already converging. Okay? So this is the actual statement of the nth term test. If the series, let's say the summation of x sub n, okay, converges, then the limit of x sub n is equal to 0. Take note of the structure of this given statement. It doesn't work otherwise. It starts with the idea that the series is already convergent, and then we can actually provide the limit of the series being equal to 0. There is no guarantee that if the resulting limit of the sequence is series is 0, then it is convergent. I'm going to give you examples or illustrations later, but first let's try to prove this given statement, nth term test. So here is a short proof for the nth term test. By the definition, okay, by definition, the if okay, or let's say let, okay, let summation of x sub n be convergent, okay, because that's the first part of a statement. This would mean, okay, this would mean that the limit of the series exists, okay, since it's already convergent. Of course, if it's not convergent, then the limit doesn't exist. So this is just the first statement that we can draw. Now, since per definition of infinite series, a while ago in a previous video, we have said that S sub k is equal to the sum of S sub k minus 1 and x sub n. Okay? This is the structure as of the partial sums of our what we call this one, series. Now, manipulating that, if we're going to subtract both sides by this term, and I'm going to use the what do you call this one, the symmetric property, I have here x sub n is equal to s sub k minus s sub k minus 1. Okay, we need to show that the limit is actually 0. Okay, so using this, if we're going to take the limit of both sides, x sub n, and this is what you would like to be shown to be 0 for this nth term test to hold, this is also true by getting the limit of the difference of s sub k and s sub k minus 1. Okay? So, going further, the limit of x sub n, we don't know this yet, but that's our goal. Okay? Applying the limit laws, so you have here the limit of s sub k minus the limit of s sub k minus 1. Okay? So, with this form now, take note that both of these are arbitrary values of partial sums, as we don't know the extent of k in k sub 1, and we are sure earlier that the limit of s sub k exists. This would mean that since both of them, okay, both of these are representations of partial sums in our series, then, and again, we are given that x sub the summation of x sub n, or the series, is convergent. This would mean that whatever would be the limit of this, that's also the limit of this form. Okay? Because they are both on the same convergent series. So if we say, if the limit of s sub k is, say, for example, L, this is also, let's write here a statement, then the limit of s sub k minus 1 is also equal to L. Then, in short, connecting to that, the limit of x sub n would be L minus L, and the limit of x sub n is equal to 0. We have shown the statement of nth term test stating that if a series is already convergent, And if you're asked about the limit of that series, automatically it's equal to 0. And we have shown the proof of that here in this video. But again, a caution, yes, if the series is convergent, the limit of the series is 0. But it doesn't necessarily tell us otherwise that if we have a limit of a series being 0, automatically it's convergent. I'm going to give you one example for that. Let us say we have here this series. This is a harmonic series, and the limit of 1 over n as n approaches to infinity is actually equal to 0. But does this tell us that this is convergent? The answer is no. Harmonic series is a divergent series. So again, this limit of a series which equals to 0 doesn't guarantee convergence, because the statement starts with convergence and then proceeds with our limit being 0. Now, aside from this, let me give you an example. We have here the limit of, let's say, 1 over n plus 1 as n approaches, that's not that limit, but the series, okay? So this is actually considered to be convergent, because actually partial sums here are bounded. I'm not going to show you that, but this is actually a convergent, okay, a convergent series. Hence, the limit of 1 over n plus 1 as n approaches to infinity is equal to 0. Automatically, this is true according to the n-term test. Again, but it doesn't say otherwise. Okay? Thank you very much for watching.